Okay, in this video, we're going to look at momentum and collisions. And in order to do that, we need to look at some of the basics of momentum, which this part you already have in your notes, I think. But anyways, momentum. Momentum is the measure of inertia in motion, or we could say it's the measure of an object's tendency to stay in motion. Two parts for momentum, or momentum is equal to two things, which is mass times velocity. Velocity is a vector, it has direction, which makes sense then that momentum's a vector and it has direction. So if an object has a tendency to stay in motion, it has a tendency to stay in motion in that direction, right? That's what it tends to do. Now, momentum goes right along with conservation of energy and Newton's laws, right? All the rules that we have for those still have to work here. This is kind of another way of looking at things, but we can't violate any of those laws, and this goes right along with that. So we could find an object's momentum by taking the mass, multiplying it by the velocity, and we'll have the momentum of that object. Now, calculating momentum is easy enough. Really, though, we need to look at the conservation of momentum, which is really where we're going to be able to use this idea and solve for certain values. In an enclosed system, the total momentum remains constant. Now, there's a couple things for that. One is we have to understand that it is an enclosed system. It says it there, right? So an enclosed system For an enclosed system, there's no outside forces, right? So there's nothing on the outside that is acting on any of the objects that are part of our system. So as soon as we have something outside, then it's not an enclosed system, conservation of momentum doesn't hold true, right? So this works well in collisions, like the title said. Anything where there's objects that interact with each other, but they're not interacting with anything else at that moment, right? So we could deal with these things. And the total momentum remains constant. That doesn't mean any individual object remains constant, but it does mean that the total, or we could say the system total, the total in that system remains constant. One object can lose some momentum, well, then that means the other object must have gained some momentum, right? So in their collision, certainly some things will slow down and their momentum will become less, but then other things will speed up and their momentum will become more. So the total momentum has to be equal. So let's look at this in terms of collision. So the first type of collision is a sticky or totally inelastic collision. And that's when two objects hit each other and then fuse together. So two objects hit and then they move as one after the collision, right? So this could be throwing something that's sticky, like throwing a ball of clay at something. When it hits, it just kind of splats on it and they move together as one. This could be some type of car accident where one car hits the other one from behind and then they just both slide forward together. But anything where they lock together and now they're moving as one. Now the general equation for that is written down here. If we find the momentum of the first object, we find the momentum of the second object, we add those up, we get a total momentum, right? And I didn't say it, but it is in your notes. But either way, momentum, the symbol for momentum is P. So we get a certain total momentum. After the collision, this has to be the same thing. The total momentum has to stay the same. It's not conservation of velocity, right? And it's certainly not a statement where one thing can't lose momentum. It certainly can. But the total momentum in the initial part has to equal the total momentum, excuse me, in the final part. So let's take a look at a situation like this. All right, so let's say we have, let's do this one. And we're even going to put some energy into this. So let's say we have a block of wood, and this block of wood is hanging from two strings, kind of like that. And this block of wood has a mass of 1.4 kilograms. And we take something like a dart, and this dart has a mass of 0.07 kilograms, so 70 grams, which would still be a pretty heavy dart. And someone threw it at a speed of 40 meters per second. So this is what's happening before. And we'll say that this dart is going perfectly horizontal for this one. And it kind of fits with this one because it's going to be on the ropes and other things are going to happen. And then the question becomes, after the dart hits the block of the wood, how high does the block swing? So this is going to be a little more than just a collision, but we're certainly going to look at the collision and conservation of momentum. So first of all, this is our enclosed system. It is the block of wood and it's the dart, and nothing else is applying forces to either one. The dart's going to hit the wood, and then they're going to move together as one. Once the dart hits the wood, it's going to be stuck in the wood, right? So this is not only conservation of momentum, but it's absolutely a sticky collision. So the total momentum initial has got to equal the total momentum final. So what is the momentum initial? Well, it is the mass of the dart. All right, dart. Plus the velocity of the dart. Sorry, D for dart. There we go. Plus the mass of the block times the velocity of the block. This is my total momentum initial. I look at all my objects, find out their momentums, and then add them together. But again, we're adding vectors. But this one, it's not going to be so bad. So what do we know, first of all? Well, we know the block's not moving before the dart hits it, so the velocity of the block initially is 0. So that's gone. And I can just then figure it out. So it is 0.07 kilograms times 40 meters per second. That is going to give me an answer of, all right, so 0.7 kilograms times 40 meters per second works out to be 2.8 kilogram meter per second. So that's the total momentum of this system initially. So it's also got to be the total momentum of this system finally. I'm writing some weird stuff, so let's fix this. I don't know why I put an M there, but this would be the total momentum final. Well, what's the total momentum final? Well, after the collision, I have just one object. I have the block and the wood together, and they're moving. I'm sorry, the block and the dart together, and they're moving as one. So if we take the mass of the dart plus the mass of the block, that's the mass of the object that's moving after the collision, and then it's going to have its own final velocity. And it's only going to be one final velocity because there's only one object now. So 2.8 kilogram meter per second is going to equal the mass of the two things together, which is going to total 1.47 kilograms times the final velocity. And let's see, we are going to have 2.8 kilogram meter per second divided by 1.47 kilograms, and I will get the velocity after the collision. So that's going to equal the final velocity, and that is going to be 2.8 divided by 1.47. This new velocity is going to be much less, 1.9 meters per second. And that's going to be to the right because the initial momentum was to the right, and the final momentum has to be to the right. Now, we're not done because we asked the question, how high does the block swing? And after the collision, the block's going to swing up. Well, now there's no more collisions. Now we're dealing with the pull of the earth. We have an outside system or an outside force that we didn't deal with before. So we can't really look at this second part in terms of collisions and momentum, but we can look at it in terms of energy. Now, just to say it, if I figured out the kinetic energy of the dart, that's 1/2 times mass times speed squared. And this dart's going to have a decent amount of kinetic energy because it's got such a high speed. So it's going to be 1/2 times 0.07 kilograms times speed squared, 40 meters per second. I'm trying to squeeze it in there. I put it in a bad spot. But I'm not going to use this number. I'm really just making a point with this number. So 1/2 mass times speed squared. 1/2 times 0.07 times 40 times 40. 0.07 times 40 times 40. The total kinetic energy at the start of this problem is 56 joules, right? And that is the mechanical energy, let's say, right? If we remember back for energy, we're looking at three types of energy: gravitational potential energy, spring potential energy, and this type of kinetic energy, energy of objects that we could see that are moving. So there's 56 joules of kinetic energy in this system. We don't know what other types there are, but we don't see anymore, and there's not much more we could deal with. It's at its lowest point, so we're going to say there's no gravitational and there's no spring. But here, after the collision, well, the kinetic energy is still going to be the same equation. One half. It's a bigger mass. Mass went up. But the speed went way down, and 1.9 meters per second, that's a 9, 1.9 meters per second, but the speed went way down. So we're going to lose kinetic energy, right? So right now I'm just making a point that during the collision, 0.5 times 1.47 times 1.9 times 1.9, there is only 2.65 joules of kinetic energy after the collision, which means 56 minus 2.65, the change in kinetic energy, final minus initial, there was 53.35 joules of kinetic energy lost. Now, this doesn't violate conservation of energy, right? There's nothing that says that kinetic energy can't be lost. So, but what really happened is it turned into other forms that we can't calculate. There's heat, there's work, there's sound, there's these other forms involved, and that's how much kinetic energy was lost in the process of this collision, right? The tip of the dart, dug into the wood, that's work. While it did that, it created heat, it created sound, right? So we know the kinetic energy is going to turn into other things, and this gives us a clue tells us exactly how much we lost. It doesn't really tell us how much of each form it took, it gets taken, and that depends on a lot of variables, right? What's the material? If it was a really hard block, like it's a block of metal, there's going to be a lot of sound. It also couldn't be a sticky collision because the dart would bounce off it. But let's say we threw it hard enough that it dug into it, there'd be a lot of sound, there'd be a lot of heat, and it wouldn't get very deep into it. If it was a soft piece of wood, well, then there wouldn't be a lot of sound, and it would push into it very deeply. So there's some variables to how this energy gets used. But the important thing is this energy is lost. Now, how high does the block swing? Well, after the collision, this block has kinetic energy. The kinetic energy after the collision, which is this value. Well, after the collision, this block's going to swing upwards. It's not going to hit anything else. There's not going to be any collisions or anything like that. So I can definitely say the kinetic energy here equals the gravitational potential energy here. So now I could use my conservation of energy because here there's no mechanical energy lost after the collision. So there's a certain amount of energy because the dart was going at a certain speed. It hits the wood. Using conservation momentum, we could figure out how fast the wood and the dart move together. And then after the collision, we can go back and use conservation of energy. And therefore, I could solve for the height because the kinetic energy is going to equal mgh, which is my equation for potential energy. Kinetic energy divided by mg equals h 2.65 kilogram meter per second squared, meter squared per second squared, divided by a mass of 1.47 kilograms, and then divided by 9.8 meters per second squared. It's going to go off the screen. Let's do this. We have all that stuff already. Let's just clear that area out, and we'll rewrite that. Kinetic energy divided by mg equals h, 2.65 kilogram meter squared per second squared, divided by 1.47 kilograms, divided by 9.8 meters per second squared. Kilograms cancel out, second squared cancel out. This meter gets rid of one of these meters, and my answer is going to be in meters. So how high does it swing? It's not going to be very far because it lost so much kinetic energy in the collision, but it's going to move. All right, 2.65 divided by 1.47 divided by 9.8. Hold on, sorry. Let me do that again. 2.65 divided by 1.47 divided by 9.8. Much better. It is going to swing up 0.18 meters, 0.18 meters, or it's going to swing 18 centimeters above the ground. So here's an example where we use both things. We use conservation momentum to deal with the collision because the kinetic energy here is definitely not equal to the kinetic energy here. These two things are not equal because we lost a ton of kinetic energy in the collision. So we had to start with conservation of momentum, and then after the collision, then we can go back to conservation of energy to see how high it swings up. So there is one example of a totally inelastic collision. Okay, example number 2, let's say that we have a blob of clay, and this blob of clay has a mass of 1 kilogram, and it's moving this way, and we'll say that this angle is 27 degrees, and then we have a second blob, and this one's bigger, 1.8 kilograms, and this one's moving more drastically where this angle is 64 degrees, and then these two blocks of clay are going to hit, and they're going to form one block, which is going to be a bunch of red, and it's going to be a bunch of green all mushed together. And then the question is, where do they go from here? Well, now if we go back to the initial situation, right? We know all the initial information. There's only one unknown in the end. So totally inelastic collisions, if we know the initial information, there is only one outcome. So as soon as we figure it out that that is the case, then we can start looking at this, and we know that this is a solvable problem. If they collide and that collision is totally inelastic, there's only one thing that could happen after the collision. So that's good. So, before they collide, this one is going 12 meters per second, and this one is going 15 meters per second. Now we have all the information. So we know the mass, we know the velocity, we can figure out the momentums. So I'll start with the green one, and the momentum is going to be 1 kilogram times 12 meters per second, 12 kilogram meter seconds. So that's the total momentum, but it's at that angle. So if I want to break this up, I'm going to break it up to its two components. Now, I didn't give you the angles in the same way, right? So I do have to be careful, but I know this is going to the right and down. So 12 kilogram meter per second times the cosine of 27 is going to give me my horizontal component, which is going to be 10.69 kilogram meter per second. That's going to be positive because it's to the right. Then I have 12 sine of 27, which is going to be 5.45 kilogram meter per second. But I also know it's going down, so I'm going to make that negative. And with the angle I gave you, I have to know that, right? I have to understand the situation, because giving you the angle of 27 could be considered a little misleading, because this one is starting with 0 to the right, but it's going up. This one's starting with 0 to the right, but it's going down. So we have to make sure we understand what's happening with the angles. All right, but the next one, I can get the total momentum, 1.8 kilograms times 15 meters per second, works out to be 1.8 times 15, 27 kilogram meter per second. Now I could break it up again, so it's going to be 27 times the cosine of 64. And it's to the right, so I'm going to make that positive, 11.84 kilogram meter per second. And again, it's positive because it's to the right. And then it is 27 times the sine of 67. That works out to be 24.85 kilogram meter per second. And that's going to be positive because it's going up. Now I can get my total initial momentum. 10.67 plus 11.84. So before the collision, the total momentum horizontally was 22.51 kilogram meter per second. And the total momentum vertically works out to be a number smaller than this, because this is a negative, this is a positive, 19.38 kilogram meter per second. So this is my total momentum initially. And it's breaking up into the two components. And yeah, I'm going to have to put it together, which I'll do next. But this is all my initial information. Now, if I want to get my total momentum, well, then it is 22.51 to the right, 19.38 up, and I'm looking for this. So finding the number, Pythagorean theorem, 22.51 squared plus 19.38 squared, add them up, take the square root of the answer, here we go. My total momentum is going to be 29.70 kilogram meter per second, and then my angle, tangent of the angle is going to be my opposite over the adjacent, so 19.38 divided by 22.51 equals 0.86. Take the inverse tangent of that. This angle is 40.7 degrees. So this is my initial momentum, and therefore it is also my total momentum. Now, I didn't really even ask a question, but let's just keep going with this. Where is this block going to go when it's done? So it is 29.7, I'm going to get rid of the funky color, 29.7 kilogram meter per second at an angle of 40.7 degrees. And I want to get the final velocity, how fast is it going after the collision? And that's going to equal my mass. Well, it's going to be 2.8 kilograms, 1 plus 1.8 times its velocity. So very similar to the last time. I know my total momentum. I know my total mass after the collision. I can get my velocity. .70 divided by 2.8. My velocity is going to be, well, after the collision, this whole block is going to be moving at 10.61, we'll say, meters per second. And what's the direction? Well, it's the same direction as the momentum. The momentum is the tendency to stay in its state of motion. So whatever direction the velocity is, that's also the direction of the momentum. So after the collision, this is how fast the two blocks will be going. And that's the direction they'll be going, which is a speed that's slower than either of the individuals, right? One was 15 meters per second, the other one was 12 meters per second. After they collide, there is a loss of kinetic energy. So again, this is a situation where a lot of kinetic energy will be lost in the forms of sound, heat, and work. And just to go back to this slide, anytime we have a totally inelastic collision, that's when the maximum amount of kinetic energy is lost. If they hit and fuse together and move as one, that's when we have the most, right? For any situation, if they bounce off each other, if they kind of just bump each other and keep on moving, right, then kinetic energy can be lost. But any collision, regardless of what direction they're coming from, how fast they're going, if they collide and fuse together and then move as one after the collision, then that is a situation where the most kinetic energy is lost. And we saw in the first one that there's a lot of kinetic energy lost. And then this one we could figure it out, but I'll tell you what, it's going to be a lot. And we know that because both of these speeds were more than the final speed. So we know there's a drop in kinetic energy. And because it's speed squared for the equation, there's a pretty big drop in kinetic energy. So there is two quick examples. All right, our next type of collision is an inelastic collision, which is different than a totally inelastic collision, because now after the objects hit, they do move apart, right? So we have two objects that hit, they bounce off each other, and then they both keep moving their own ways. Kinetic energy is still lost. It's just not going to be as much as a totally inelastic collision. So for an inelastic collision, kinetic energy is lost in the forms of heat, sound, work, and things like that. But the objects do separate and go their own ways, right? Again, most examples of car accidents would be that, right? They hit, and then after the collision, they both go their own separate ways. They don't move as one. They go in different directions. You know, a rubber ball hitting something is another example, or things like that, where they just don't stick together. They move apart. All right, so what would the equation be? Well, I would have one object, m1 times its velocity. That would be my initial information for the first object, plus the second object, what's its momentum, m2 times its velocity. And again, this would give me a total initial momentum. And that's going to equal the total final. But now I have more things that might not be known. So the mass, we're assuming, doesn't change. And then this would be m1 final. And then m2 and times its velocity and the velocity of 2 final. And this would be the total momentum final. Now, the difference with this situation is if we go back to a totally inelastic collision, right, we know the masses. So that means we know the total mass after the collision. We were given these. So if we know all the initial information for a totally inelastic collision, there is only one result after the collision. But this one, there's more unknowns, right? If we look at it, well, we have this and we have this. We have two different things that are variables in this case. So if I know my initial information, if I'm like, okay, I know how fast, the first object was going in its mass, and I know how fast the second object was going in its mass, I still can't figure out what's going to happen to the two of them after the collision because there's just simply too many variables that we can't deal with. So we have to know some of the initial information and we have to know some of the final information in order to solve one of these situations. We'll do that in the second video.